Section 8.6, Geometry of Matrix Operators. If T from R2 to R2 is multiplication by an invertible matrix, then the image of a straight line is a straight line, the image of a line through the origin is a line through the origin, the images of parallel lines are parallel lines, the image of the line segment joining points P and Q is the line segment joining the images of points P and Q, and the images of 3 points line a line if and only if the points themselves line a line. Let's do an example. According to this theorem, the invertible matrix A maps the line y equals 2x plus 1 into another line. Let's find the equation of the other line. So how about we let xy be a point on the line that we were given, y equals 2x plus 1, and we'll let x prime, y prime be its image under the transformation A, under matrix A. Okay, so that means that x prime, y prime, the vector, can be written as A, 3, 1, 2, 1, multiplied by xy. So that means that xy is equal to the inverse, 3, 1, 2, 1, multiplied by x prime, y prime. You just multiply both sides by the inverse, and then the inverse cancels this because the identity, so we get xy by itself. Okay, so doing that multiplication, we get, or just taking the inverse really, we get 1 minus 1 minus 2, 3. Just swap, make negative, divide by the determinant. And that multiplies by x prime, y prime still. So that means that x from the left, right, is equal to x prime minus y prime by multiplying, right? You get x prime, y prime, and we get that y, reading from the left, is equal to minus 2 x prime plus 3 y prime. So if y equals 2x plus 1, that implies that minus 2x prime plus 3y prime, replacing y, must be equal to 2 times what x is, but x is x prime minus y prime, so it must be 2 times x prime minus y prime plus 1. So that gives us, by solving for y prime, that y prime must be 4/5 x prime plus 1/5. Let's sketch the image of the unit square under multiplication by the invertible matrix A given. We'll label the vertices of the image with their coordinates and number the edges of the unit square and their corresponding images. So first, let's see what happens to the corner 0, 0. So I'll take the matrix 0, 1, 2, 1, and multiply it by the first corner of the square, the first vertex, and I'll get 0, 0. So the origin stays the origin. Let's see if I can draw that. Maybe I'll need a little more space, maybe over here. So here's y, here will be x, and I'm going to make it a little shorter. I'll put 0, 0 right here. And then this will go to a new coordinate plane. So here's x, here's y, and it stays at 0, 0. So 0, 0 is still 0, 0. And while I'm here, I might as well draw the rest of my square. So all right, that's supposed to be a square. Maybe I'll move this one a little bit. Okay. And this will be 0, 1. This is 1, 1. This is 1, 0. And it connects like that. So how about we call this edge number 1, edge number 2, edge number 3, and edge number 4. And somehow this square is going to be transformed via A. We figured out that 0, 0 goes to 0, 0. Let's see what 1, 0 goes to. So I'll take 0, 1, 2, 1, and multiply that by 1, 0. And I'll get 0, 2. So it moves all the way up over here. Here's 0, 2. So that means that I went from here to here, and I ended up from here to here, because 1, 0 got moved to 0, 2. It moved all the way up over there. So this was 1, and now this is 1. Let's keep going. Let's see what happens to 0, 1. So if I take 0, 1, 2, 1, and multiply it by 0, 1, then I'll get 1, 1. So I'll end up over, let's say around over here. Maybe a little more. Okay, that's good. So that's 1, 1, and that was going from 0, 0 to 0, 1. So that means that from here to here is number 4. Okay, we'll finish up by seeing where our last vertex goes. So from 0, 1 to 1, we'll multiply that by 1, 1. That was our last vertex, and we get 1, 3. So 1, 3 is all the way up over here. So we can connect these, and we get a little parallelogram. So from, let's see, we had that from 1, 0 to 1, 1, 1, 0 went to 0, 2. So I have 0, 2. And then somehow 1, 1 ended up at 1, 3. So 0, 2 went to 1, 3, when 1, 0 went to 1, 1. So this is number 2. And you can see that this last one will be number 3, because 0, 1 went to 1, 1, 1, 1 went to 1, 3. So yeah, this is number 3. So it looks like every line that went horizontal in my original square ended up going vertical in my parallelogram image, because this went to over here, this one went to over here, and so on. So we have a table of different operators and the standard matrix that produces them and the effect that they have on the unit square. So a reflection about the x-axis, you just take the y and you multiply it by -1, and that'll flip it upside down. Similarly, a reflection about the y-axis, that x gets multiplied by -1, the first row, and it moves about the y-axis. It reflects. And then for y equals x, you just swap out x and y. So instead of them being along this diagonal, they are along this diagonal. For the orthogonal projection onto the x-axis, So that takes whatever you have floating around over here and it projects it downwards. So if it's above, it just goes straight down and it ends up on the x-axis. All you have to do is just zero out your y-coordinate, and that makes everything one-dimensional. Similarly, you can project onto the y-axis by zeroing out your x-coordinate. You can rotate about the origin through a positive angle theta by multiplying by the matrix cosine theta minus sine theta, cosine theta. We also have expansions and compressions. So you can expand in the x direction with factor k, where k is bigger than 1, by just multiplying the x by k. And similarly in the y direction by multiplying y by k. So multiplying by x by k stretches this way, and y by k stretches vertically. You can also compress if you multiply by a fraction, so something smaller than 1. And then it'll either shrink it horizontally or vertically, depending on whether it's x or y. You can also shear by inserting a constant into one of the zeros. So if you have a positive k, it shears in the positive direction. It just like kind of slants it. If you have a negative value for k, it shears in the negative direction. And if you put it on the left corner, that constant, then instead of shearing left to right, it starts shearing up and down. As an example, how about we find the standard matrix for the operator in R2 that first shears by a factor of 2 in the x direction and then reflects the result about the line y equals x. We'll sketch the image of the unit square under this operator. So let's find the first matrix to shear this thing by a factor of 2. So that's just 1, k is 2, 0, 1, because it's in the x direction, so it goes in the upper right corner. And then our second matrix is the reflection about the line y equals x, so we'll just swap the ones along the other diagonal, because we're swapping x and y. So then our transformation is what we get by multiplying these matrices. So I'll take a2 times a1, so that a2 is done afterward. That'll be 0, 1, 1, 0 times 1, 2, 0, 1, and we get the matrix 0, 1, 1, 2. So I'll draw what happens after a1 to the unit square. So first, starting with the unit square, here's 1, 1, here's x, and I'll shade a little bit so you can see what happens to the shaded part. So then this is mapped via a1 via a shear, so that means by a factor of 2. Let's see, it'll get pushed over something like this. And then here's the shaded part. Something like that, where this is 3, 1. It's moved over 2. And what I'll do is I'll then reflect this about the line y equals x, and that'll produce our final result. Okay, so here's y equals x. And that means that we end up over here. Where this is 1, 3. And notice the shading flips to the other side. Let's find the standard matrix for the operator R2 that first reflects and then shears. So we'll do it in the other way. So we'll take a1 and multiply that by a2. So first we want 1, 2, 0, 1. That needs to happen afterwards, so multiply that on the left. And then we want 0, 1, 1, 0, which gives us the matrix 2, 1, 1, 0. And we'll see what happens here. We'll start with the unit square again. So here's 1, 1. Do a little more shading. That'll be transformed. And this is where the shading comes in handy, because the square looks the same when you reflect it over the line y equals x, right? Except that the shading is in the other direction. The shading gets reflected. And then we'll shear it. So let's see. Our shear. Okay, here's y equals x again. And we'll something like this. Maybe. Okay, I'll take that. So it just gets stretched out. So over here is 3, 1. And you can compare it. See how it's floating over there, so the order definitely matters that you do these operations in. Let's confirm that the shear and the reflection in parts A and B do not commute. Well, clearly, A1 multiplied by A2 is not the same as A2 multiplied by A1. Not surprising, since matrix multiplication in general doesn't commute. We have a couple more operators. We can have a contraction with factor k in R2 if we replace the 1's with k's, and so multiplying by a fraction, it'll shrink the unit square or whatever we're applying our operator to. And we can also dilate by making these bigger than 1, multiplying them. So how about we discuss the geometric effect on the unit square of multiplication by a diagonal matrix A, in which the entries k1 and k2 are positive real numbers not equal to 1. Well, clearly if the k's are equal, k1 equals k2, then by the above table, we have either a contraction or a dilation. Otherwise, let's write out matrix A. So that's k1, 0, 0, k2. But we could separate that as 1, 0, 0, k2 multiplied by k1, 0, 0, 1. So that implies that it's actually can be viewed as a compression or expansion, depending on k, in x, followed by a compression or expansion in y, as we saw in the other examples in the other tables. Let's now discuss the geometric effect on the unit square of multiplication by the matrix A, given over here with negatives. So again, we should rewrite A. So, I mean, you can kind of see that this is going to be a reflection about the origin, because it just has these negatives over here. But we can still rewrite A to view it in different ways. So first you can see that it's a reflection about the origin. But by separating A out, So it's minus 1, 0, 0, minus 1 into minus 1, 0, 0, 1 times 1, 0, 0, minus 1. Then you can see it's actually also a reflection about the x-axis followed by a reflection about the y-axis. And it makes sense because composing these two reflections is the same thing as reflecting about the origin, right? It just takes the unit square. So if I draw it like right over here, and do a little bit of shading, then it just takes it and moves it right here. Right? It's the same thing as reflecting and then reflecting again. It's the same thing as just doing one reflection about the origin. Two different ways of looking at the same thing. How about we now discuss the geometric effect on the unit square of multiplication by the matrix A right over here. Notice the minus 1s are on the other diagonal now. Okay, well, it shouldn't be too difficult to see that all this is going to do is just reflect over y equals negative x. Right? I'll just have my unit square over here because it swapped x and y and it made them negative. So I'll still end up over here. I just have reflection. And so notice the shading is actually different here. You have to be kind of careful. You can think of this thing as kind of reflecting here and then reflecting here. So the shading is kind of in the same direction, but over here you have to think of it as reflecting about this line. So this line becomes this line, whereas in example 5 that wasn't the case. It wasn't like this line jumping over here, otherwise I would have drawn the shading like this. So even though the shape looks exactly the same, I guess if there was more characteristics of it, or if it wasn't so symmetrical, then it'd be more apparent that there's some shenanigans going on. If E is an elementary matrix, then TE from R2 to R2 is one of the following: a shear along coordinate axis, a reflection about y equals x, a compression along coordinate axis, an expansion along coordinate axis, a reflection about a coordinate axis, or a compression or expansion along coordinate axis followed by a reflection about a coordinate axis. Shouldn't be super surprising. Remember that the elementary matrices were from a single elementary row operation applied to the identity matrix. So that means that the matrices, the elementary ones, must have one of these forms. The first two matrices represent shears along the coordinate axes. The third represents a reflection about y equals x. If k is greater than 0, last two matrices represent compressions or expansions along coordinate axes, depending on whether k is smaller than 1 or bigger than 1. If k is negative, and if we express k in the form of k equals minus k1, where k1 is positive, then the last two matrices can be rewritten. Right? We just take k, rewrite it as minus k1, and then you can separate off that minus and you can see what's happening. And it's really just a product representing a compression or expansion along the x-axis followed by a reflection about the y-axis. The second one represents compression or expansion along the y-axis followed by a reflection about the x. In the case where k is negative 1, these transformations are simply reflections about the y-axis or x-axis. If TA from R2 to R2 is multiplication by an invertible matrix A, then the geometric effect of TA is the same as an appropriate succession of shears, compressions, expansions, and reflections. Again, not super surprising. We just break it down into all of the different possibilities. You just write the matrix as a bunch of different factors. In example 2, we illustrated the effect on the unit square of multiplication by this matrix A. Let's express this matrix as a product of elementary matrices and then describe the effect of multiplication by A in terms of shears, compressions, expansions, and reflections. So if we have 0, 1, 2, 1, then we want to get back to the identity. So we could swap the rows, get to 2, 1, 0, 1, and we can get a 1 in the first row by multiplying by a half, dividing by 2, whatever. So 1/2, 0, 1. And then we would get to the identity by adding minus half of the second row to the first row. So we get 1, 0, 0, 1. So the first matrix would be, first elementary matrix that we would use to get to identity would be 0, 1, 1, 0 to flip the rows. The second one would be half, 0, 0, 1 to divide the top row by 2. And then the third elementary matrix would be 1 minus half, 0, 1 to get rid of that minus half. So that means that A can be written as these 3 elementary matrices in succession, but we want to go backwards. So E3 should happen first, but remember we're going backwards. We want to have E3 inverse to get to A, because this is what you would result from the application to the identity. So if we take E3 inverse, multiply it by E2 inverse, multiply it by E1 inverse, that is how we could build up A. So that means we build up A by taking 0, 1, 1, 0 times 2, 0, 0, 1 times 1/2, 0, 1. So let's write out what each one does. Number 1 is shearing by half in the x direction. Number 2 is expanding by 2 in the x direction. And number 3 is reflecting about y equals x. So let's see if we can draw these. Okay, let's start with the unit square. So it's 1, 1. And here's a little shading. And then that gets sheared in the x direction. So it becomes, well, something like this. Here's 3 over 2, 1, sheared by half. And then it gets expanded. So let's see if we could do that. So I should somehow make a bigger one. Let's see if I can do that. So here's 3 now, because it gets multiplied by 2. And then I have to reflect this about y equals x. So I might as well just draw that. Here's y equals x, and I'll flip it over that. Let's draw y equals x again. Okay, so flipping, I'll draw it up here. Something like this. So here's 1, 1. 0, 0 is the origin. This becomes 1, 3 instead of 3, 1. So this is 0, 2. And here's our final result. The effect on the unit square by this transformation. The right-hand rule can be used to establish a sign for an angle of rotation about a unit vector u by cupping the fingers of your right hand so that they curl in the direction of rotation. If your thumb points in the direction of u, right over there, then the angle of rotation is regarded to be positive relative to u. If it points negative in the direction opposite to you, it is regarded to be negative to you. It points in the direction opposite is negative. Okay, so we have our last table where we have different operators for rotations. They could be counterclockwise about the positive x-axis through an angle theta, in which case we have that same rotation matrix stuck in. We just have zeros and a 1 for the x built around it. And then similarly, if we're rotating about the y-axis, then the y gets the 1, and about the z-axis, then the z gets the 1.